Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, lecture 7.2, Composition of Rotations, part of the chapter 7, Rotation Matrices. Okay, so the nav over here. Let us consider the problem of how to compose rotations. It is easy to see that to compose rotations, we multiply the corresponding rotation matrices. There are, however, two problems. First problem, the order of multiplication matters, and so it is not clear in which order the rotation matrices should be multiplied. Second problem, the information first rotate the body by r about axis 1 and then by r about axis 2 is ambiguous in the sense that it is not clear with respect to which frame the second rotation r2 is expressed. For example, looking at figure 7.2 right here, consider a body, an aircraft in this case, with initial reference frame sigma 0 as it does in this figure. Assume sigma 0 is a fixed or inertial reference frame and rotate the body about the y0 pitch axis. It's this one, right? So the y0 axis, we're going to rotate it about this axis. So this y0 axis, we'll rotate it nose up, okay? Positive. Because sigma 0 is fixed, we introduced the new body fixed reference frame sigma 1 that moves with the body, satisfying the following equalities and inequalities. y1 is equal to y0, meaning that the y-axis of sigma 1, the reference frame 1, is the same as the y-axis of reference frame 0. Okay, so the rotation was about y, so we keep that y-axis the same, but there's going to be a new z-axis and a new x-axis, okay? We call sigma 1 the successive or body reference frame. We're going to use that a lot, and it's very important to make the distinction because this rotating frame or successive frame or body frame, body fixed frame, body reference frame, all of these terms mean the same thing. It's shown here, it moves with the vehicle. So in this case, we have a positive pitch that has occurred. And so our old x naught is still shown in gray here below, but our x1, so x0 is down here, x1 is pointed with the nose of the aircraft. And z1 has rotated as well. Okay, so we see the z1 rotation. And then we see that y1 and y0 are the same because that axis about which the aircraft rotated is going to be left alone in the body fixed frame, but only when we rotate about that specific axis. Okay, so if you are now asked to rotate about the z-axis, it is necessary to know whether that is the z0 or the z1 axis that you're referring to, i.e., whether the second rotation is expressed in the fixed inertial frame or in the successive body frame. Thus, if we consider the statement, rotate about y by pi over 6, then rotate about z by pi over 3, because we like to rhyme, right? We can use the formulas for the basic rotations to compute the two rotation matrices, but is the composite rotation about y by pi over 6, then rotation about z by pi over 3 in the sense of this one is first to be written, so left multiplying this one? Or is it just the opposite, rotation about z first, then y? So, problem 8.3, let's look into it a little bit more. Composition of rotations. Given a rigid body and two rotations represented by the matrices R1 and R2, suppose we first rotate the body by R1, then by R2. What information do we need and how do we compute the resulting rotation? The following theorem will provide us with the answer to this question or problem 8.3. So theorem 8.4, which we call post-multiplication if successive frame and pre-multiplication if fixed frame theorem. It's a mouthful. It's almost as long as the theorem. The composite rotation is either R1 then R2 in terms of matrix multiplication, or R2 R1. And it's the first one, R1 R2, if R2 is expressed in successive or body frame, meaning that if the R2 rotation is written relative to a reference frame that is body fixed or successive, then this is the order of multiplication. If, on the other hand, you are expressing both of them in a fixed inertial reference frame, the same reference frame, R2 and R1 are flipped in the order of multiplication. Hence, here is the solution to our example. If the statement is rotate about y0 by pi over 6, then rotate about z1 by pi over 3, notice now we've specified which y-axis and which z-axis, and the z-axis is now a successive reference frame. See the z1 here? Then the composite rotation is rotation about y, pi over 6, then rotation about z, pi over 3. And instead, if the statement is rotate about y0 by pi over 6, then rotate about z0 by pi over 3, z0, okay, that's the inertial fixed frame, then the composite rotation is rotation z, then rotation y. So that's the ordering. Now, I mean, this is just a theorem. It's not been proven at this point, but at least it's a clear statement of how to deal with this. And we aren't in the practice of giving you theorems that are false, or at least theorems that are not yet proven to be false. So I think we're going to be okay with it. To rigorously understand this theorem, we study two problems of independent interest. One, given three reference frames, and given the reference frame rotation matrices R1, 0 and R2, 1, what is the reference frame rotation matrix R2, 0? Okay. And two, given a rotation expressed as a rotation matrix R in the reference frame 0, what is the representation with respect to the second reference frame, sigma 1? So let's look at problem number 1 first, this first consideration. Composing reference frame changes. Given three reference frames and the reference frame change matrices R1, 0 and R2, 1, what is the frame change matrix R2, 0? By definition of reference frame rotation matrices, we write that you can take a point P1 and rotate it to the reference frame 0 to represent it in the reference frame. So this P0 and P1, they are the same point represented in different reference frames. Also, you can do the same thing for a point that's expressed in sigma 2 and express it in sigma 1. And finally, you can do the same thing for a point in 2 and express it in sigma 0. Composing the first and second equalities, so this one and this one together, we see that you can say P0 equals R1, 0, P1, and P1 is equal to R2, 1, P2, so you can just plug this second equation into the first equation to get that P0 is equal to R1, 0, R2, 1, P2. And in turn, we obtain the desired result because whatever matrix this is by definition R2, 0, because it takes a point from reference frame 2 and it gives us the representation in reference frame 0. So we see that R2, 0 is equal to R1, 0, R2, 1. From these calculations, we learn two lessons, as discussed in remark 6.4 for rotation matrices in the last chapter. Subscript and superscripts play a critical role. For example, see the correct relationships. 1, P0 is equal to R1, 0, P1. Remember, subscript, superscript have to match. R2, 0 is equal to R1, 0, R2, 1. Subscript, superscript have to match. This is another way of helping us make sure we have the right order of things. 2, when the second rotation is expressed with respect to first rotation, which is the case here because we used the matrix R2, 1, then the second rotation is equivalent to a so-called rotation expressed in a successive frame. And the final composite rotation is obtained by post-multiplying or right multiplying the second rotation. Problem number 2, representing a rotation in a different frame. Given a rotation S expressed in frame sigma 0, what is its representation with respect to sigma 1? Okay, how do you change reference frames for a given rotation? Let us write down the facts we know. You can rewrite P1 in reference frame 0 with this relationship. Rotation in sigma 0 is S, hence rotated point Q0 is S times P0, and Q1 is equal to R01 Q0. So, putting these facts together, we calculate that Q1 is equal to R01 Q0, which was the last of these statements of the facts that we know. We can then substitute in what we know about Q0, which is that it is equal to SP0, as we do here. And we can also write what we know about P0, that it can be written from P1 using the R10. And finally, we can write this as our composite equality, where we've flipped the 0 and 1 here and transposed this matrix, which is equivalent. So you can flip these indices via a transpose as we have done before. So this transformation is how we can represent a rotation in another reference frame. Hence, the same rotation has two different expressions as a rotation matrix when expressed in different frames, as we would expect, right? Rotation in frame sigma 0 is S. If we want to express that rotation in frame sigma 1, then we have to use the transformation from 1 to 0, the frame transformation from 1 to 0, transpose it, and multiply S, left multiply S, and then right multiply S by the same transformation, without the transpose this time. Okay, here is the geometric interpretation of this result. Given that S is the rotation expressed with respect to sigma 0, you rotate a point P, expressed as P1, with respect to sigma 1 by doing 3 multiplications. First, express P with respect to sigma 0 as R0 P1. So now we've moved P from reference frame 1 to reference frame 0. Second, rotate the point R10 P1 to obtain this rotation. Remember, S is a rotation in the 0 frame, so we can now rotate. And third, express the resulting point back with respect to sigma 1 as this expression. So what we effectively did is move to the 0 reference frame, rotate, and then move back to the second reference frame. Okay. Another example here. Given sigma 0, define sigma 1 by x1 equals y0. So what does that mean? It means that we have defined the x1 axis, that is the first of our basis axes, as the same as our old y-axis. So our new x-axis is the old y-axis. The 1 x-axis is the 0 y-axis. y1 as z0. So we're going to use the old z-axis to be our new y-axis. And our old x-axis is going to be our new z-axis. Okay? So verify that sigma 1 is right-handed. We're only going to use right-handed coordinate systems in our formalism. So note that, you can verify this by noticing that none of the basis axes is changed. Sigma 1 is not a rotation about a basic axis of sigma 0, because if you rotate, you're going to move the other axes, right? Now, consider a rotation S about the vertical axis Z0. Okay, so this is in the 0 frame, which is expressed as S equals a rotation about Z of theta in the sigma 0 frame. The rotation S and the two frames are depicted in figure 7.3. Okay, so this is down here, and we see the 0 frame on the left and the 1 frame on the right. We have this rotation about the Z0 axis S that's shown here, and we're going to look at it in frame 1 as well. So good. So we now write R10 and show that R10 transpose, rotation about z of theta, R10 is equal to the rotation about y in the one reference frame. So this is a little bit deceptive, and in fact, below I use the subscripts associated with which reference frame we're using. So this rotation about z is in the 0 reference frame. This rotation about y is in the 1 reference frame. We're going to show that this is equivalent. What we're doing is we're effectively verifying this formula for a given S, okay? So that is that. All right, the rotation. Okay, so R10, here is the transformation. So it's fairly easy to write our new axes in terms of our old axes because we just effectively swapped them. Okay, we did, I'll use my right hand, we did this kind of action. So we can essentially read off these columns, R10 columns. The new x-axis is the old 0, 1, 0 axis, which is to say y0. The new y-axis is the old z-axis, right? And the new z-axis is the old x-axis. So that's what defines this reference frame transformation matrix. And we will then just go ahead and plug that into our formula and calculate this. So a little bit of matrix multiplication later, you get this representation here, which is a rotation about the y-axis. But we have a rotation about the y-axis expressed in the y1 frame at angle theta. So that shows this equality here. This answer makes sense because rotating about the z-axis in the sigma 0 frame should be the same as rotating about the y-axis in the sigma 1 frame, since we defined them to be the same axis. So we defined z0 to be y1. So if S is a rotation about the old z0, it should be a rotation about the new y1, as it turns out to be. So we're just verifying that that is the case, mostly for our own understanding. Proof of Theorem 7.4, speaking of understanding, we are now ready to understand Theorem 7.4, which was miraculously from the sky. It told us about the order of our multiplication. We assume the reference frame sigma 0 is rotated by R1 into frame sigma 1 so that R1 is equal to R10, which is to say R1 expressed as a rotation in frame 0. First, if the rotation matrix R2 is expressed in the successive body frame, then we are in a situation analogous to problem number 1. R1 rotates sigma 0 onto sigma 1, and R2 is expressed with respect to sigma 1 and represents a new frame sigma 2. In this case, the composite rotation is, again matching subscript and superscript, R10, R21, which is R1, then R2 in terms of matrix multiplications. Second, if the rotation matrix R2 is expressed in the fixed inertial frame, remember that's the other option, then we need to change the reference frame it is expressed in. In other words, the second rotation is R2 when expressed with respect to sigma 0, and we wish to express it with respect to sigma 1. In this case, the second rotation expressed with respect to sigma 1 is this transformation. We're going to transform this rotation from the sigma 0 reference frame to the sigma 1 reference frame with this transformation. Hence, the composite rotation is R10 dotted with this transformed R2, which gives us R2 R10, which is just R2 R1, which shows us the other options. So R1 R2 in the case of a successive body frame, R2 R1 in the case of a fixed or inertial reference frame. Okay, so that was the proof, and that was the end of this section. So I'll see you next time for parameterization of rotation matrices, Euler angles, and roll pitch yaw and all that. So see you then.